Today in Biostatistical Collaboration, I'm going to be providing an introduction to Unix, or the Linux operating system. This is the operating system used by the Ohio SuperComputer Center, which I will be calling OSC. Why use a supercomputer? So a cluster is a group of computers or nodes connected by high-speed network that form a supercomputer. A node is equivalent to a high-end workstation, which is just part of a cluster. A core is a processor or CPU, and there are multiple cores per processor chip. So when analyzing large data sets, often your personal computer or your laptop may not have sufficient memory for processing the data. However, a supercomputer that has multiple cores, nodes, and clusters would be able to handle large data sets. Some methods that you want to apply may be computationally intensive, and you may benefit from parallel computing. Also, when performing simulation studies, such as for your thesis research or for publications, you may not want to tie up your personal computer or laptop for days, weeks, or months. So you can submit jobs to a supercomputer and let the supercomputer do the processing. Also, you may sometimes need to use a particular software program that's only available in a cluster environment. Unix or Linux is the operating system on most supercomputers, like those at the Ohio SuperComputer Center. Additionally, a Mac operating system is pretty much a Unix operating system. So how do you get an Ohio SuperComputer account? Your faculty research advisor can apply for an account. They can then add you as a user to their account. So once you have an account, how do you get started? You're going to need a secure shell file transfer protocol application, as well as a secure shell client. These differ depending upon whether you're working on a Unix machine or a Mac. So an SFTP protocol, this is a secure shell file transfer protocol. This is a client that allows you to transfer files between your workstation and the shared file system on a supercomputer in a secure manner. You can also transfer files from the supercomputer back to your workstation. OSC recommends a couple of different programs: FileZilla, which the link is supplied here, or CyberDuck can be used as an SFTP client. To transfer files, you use your preferred SFTP client and connect to sftp.osc.edu. In order to access the command line version of the Ohio SuperComputer clusters, you're going to need a secure shell program. So this is used to communicate to the server in an encrypted way so that the communication is secure. OSC recommends PuTTY or Secure Shell for Google Chrome. If you download and install PuTTY on your Windows machine, you would access the supercomputer by specifying your username. Because you are at OSU, your username is going to have the following format with the @ sign and then the cluster name .osc.edu. I typically use the cluster Owens, and so I've put owens.osc.edu. You may also be able to access the supercomputer via Windows Vista or Windows 7 Remote Desktop. To do so, go to All Programs, Accessories, and then Remote Desktop Connection. When accessing the supercomputer using a Mac, you can simply open the terminal window and log in by issuing the following command: SSH-X, your username, again, this is going to be OSU @ owens.osc.edu. Note this -X. You can only use this option if you have Xcode installed on your Mac. It allows you to work with the supercomputer in a somewhat GUI fashion. To transfer files via SFTP, you can simply enter SFTP followed by your username at the cluster name that you're using, .osc.edu, in the terminal window. In either case, once you've entered this, you'll be prompted to enter your password. You can also map a drive by pressing Command K and entering the server address shown here, then clicking on Connect. You'll be prompted then to enter your OSC username and password in order to log in. OSC has also developed a web portal interface, which is at ondemand.osc.edu. This web-based user interface is usable from computers, tablets, and even your smartphone. The nice thing is you don't need to include or install any software on your Windows machine. You also don't need to access the OSC system through the terminal window. You can simply access the system in a very graphical user interface, that's GUI fashion. So you only need the ondemand.osc.edu website as well as your username and password. This GUI interface allows you to have interactive sessions. It allows you to have file access, perform job management. You also have access to visualization applications, and there's a tutorial for using this service located at osc.edu/ondemand. So I'm going to be going over several different Unix commands. There's a very nice tutorial provided at this link that I've noted here. So when looking at Unix commands, there are a number of things that are commands that deal with working with files and directories. Of course, sometimes we just want a clear screen, so clear just clears the screen of any printed output. If you want to see what working directory you're currently in, you use pwd, which actually stands for Print Working Directory. Similar to R, the ls command will list all of the files and directories in your current working directory. If you follow ls by -al, you will get a list in a very nicely formatted fashion. mkdir stands for make directory. So in order to keep your file system clean, you often want to make directories for specific projects. Some projects may have lots of different subdirectories as well. That will make your workspace very clean. Once you have different directories made, you need to change to a directory in order to work with the files in that directory. cd is the command for changing the directory. You can, of course, copy files, which is cp. And if you need help in the Unix system, man stands for manual, and you can type man followed by any command, and you will get the complete help for that Unix command. If you want to move a file, you use the mv command. The syntax is move the old file name followed by the new file name. Notice that in order to move a file, you have to have ownership of the file. rm removes a file. Be careful using this. There is no backup. So when you issue rm, it will remove the file. It's gone. There is no trash. Likewise, sometimes you want to remove directories to clean your workspace. So rmdir will remove a directory. Note that it only removes a directory if that directory is empty. You can put rmdir -R, which is a recursive way to remove all of the files in the directory followed by removing the directory itself. Just be careful when using rm and rmdir because again, there is no trash. So the first thing that I want to do is to show you how to transfer files for this course to the Ohio Supercomputer or some other supercomputer center. So I'm on a Mac, and because I'm on a Mac, I'm going to use the sftp command followed by my username at the cluster that I want to use. Again, I use owens.osc.edu. Notice that once I hit enter, I'm going to be prompted to enter my password. So I get a prompt that says SFTP. So I can look at where I am. I'm in the remote working directory, which is users. This is the project number, and this is my username. Now what I want to do is I have files located in a desktop folder that I want to transfer to a directory here. So I'm going to use a lcd command. This is to change the local directory. Okay, so I'm going to change the local directory to desktop Unix. I don't need the quotes, but if I had a long file name structure that especially had spaces in it, I need to surround that directory in quotes. So I tend to become in a habit of doing that. In order to see your local working directory, you type lpwd. So you can see my local working directory was successfully changed from users.archer.43. This is my traditional directory that is the default, and I have successfully changed to this local directory. So what I want to do is look at the files in my local directory. So I use ls. Okay, so it's like list, but I precede that with L for my local directory. And I see that I have a number of different files that are in my local directory. What I want to do now is I want to transfer those files from my local directory to the Ohio Supercomputer. So I can use the put command. The put command followed by an asterisk will actually copy each file in my local directory and put it in my directory on Owens. I can check that those files are there by typing lsal. Again, this is going to list the files in my Ohio Supercomputer current working directory. Now I have a lot of files here, so I'm going to do something like this. And you can see that my files did get copied. Once I'm done, I can type exit. I'm going to now clear my workspace. All right, so I'm at a point where I can now enter the Ohio Supercomputer by accessing it through a command line using the secure shell script. Again, I'm prompted to enter my password. And every time that you log in, for the first time, you're given a lot of information. These are news updates. Sometimes it will tell you that there is routine maintenance that's going to be planned. You'll see here that there's OSC support during the COVID-19 crisis. They are giving people free resource units to use. And so you can scroll through the news to see what's going on. You can also check the status of your resource units that have been used and how much memory you have left. I find that this is fairly cluttered, so I like to clear my screen. All right, so starting with the clear screen, we might want to see where we currently are in our file system on our Unix account. Again, PWD stands for Print Working Directory. This is your home directory right here. This is my home directory, which is of the form users/project number/your username. So don't ever touch the home directory. The nested hierarchy of folders and files on your computer is called the file system. And the root directory is the most inclusive folder on the system, and it serves to contain as a container for all of the other files and folders. So when working at the command line, your view of the file system is always based on the directory that you're currently in. So this pwd command lets you figure out where you are. Again, it stands for print working directory. The written description of where something is located in the file system is called the path. The path is a list of directory names separated by slashes. In the Unix system, the separator is a /, not a \. Paths can refer to files or folders. So again, we might want to view the contents of our current working directory, and we use the ls command to do this, which is short for list. So I do have a lot of files that are located in here. Because I use the supercomputer system quite often. If I want a nicely formatted list, I usually say list followed by the options -al. Dash in Unix usually means everything that follows is an option. So now I can see not only the files named, but whether the file is a directory or a file. So notice I have some directories here. Anything that begins with a D on this far left-hand side indicates a directory. We're going to be talking about permissions a little bit later. And you can see this is my user ID. This is the project number to which it belongs. You can see the file size and when things were created. And then you can see the file or directory names. I'm going to clear this again. Now, what I want to do is I want to make a new directory for this particular lecture. So I'm going to say mkdir, and I'll just say mkdir Unix course. All right. So if I want to then change to that working directory, I'm going to say cd Unix course. If I list what's in that directory, notice that it is blank. Now, when you're creating new directory names, it's best to not have any directory names that have spaces in them. And so you can actually create what looks like a space by including like an underline or a dash. Whenever you have spaces in your directory name, you have to be very careful when you're changing to that working directory to include that name in quotes. All right. Now, noticing that this file is empty, we want to copy files that we moved using sftp to this directory. So in order to copy it, we need to know the file's present name and location. That's known as the source. And we also need to know the location where we would like to copy the file to, or in other words, where we want the file to end up. That's the destination. Notice that the tilde command is short for your home directory. So if I say ls tilde, I get everything that's in my home directory. So I might want to copy from my home directory the files that I just moved here. And I'll tell you what they are because I actually know which ones I moved here. So I'm going to copy the 16S microbiome file, as well as the 16S temp file. So notice what I'm doing. I'm using the CP for copy, and then I'm specifying the location, which is my home directory, followed by the file name. And I want the file name to be given the same file name, so I've just copied that here. I have a few more files to copy. One is this GSE 3189.r data. That is a workspace that we're going to be looking at. I also have this D1E FPKM tracking file. I also have a PBS script, and I have an R program. Okay. Everything else can stay in its own home directory. I'm not going to be using those any further. All right, so if I want to see what's now in my current working directory, which is my Unix course directory, I have successfully moved my files there. Now, I could have come into what I normally would do, in fact, I would have come into Unix using my SSH login. I would have created the Unix course directory. I would have then exited, gone back into the operating system by using the SFTP client, and then I would have transferred my files by changing my cluster working directory to Unix course and my local working directory to desktop Unix, and then moving my files from my desktop into my Unix course folder. That would have prevented the need for me to copy these files from my home directory to this Unix course directory. I'm just demonstrating how you can copy within the SSH client should you need to do so. Again, if you need help on any topic, you can use man followed by the CP or whatever Unix command that you want. Once you hit enter, you get a lot of information about all of the different options that you can supply to the command. It's quite a lot usually. Once you're done looking through the help for whatever command you're looking at, you can simply type Q, which quits the help page. Sometimes you might have preferred to move the file rather than copy it. In that case, you would have used the MV function. Now, I have some more information that I wanted to share about the structure of your different directories. So the current directory that I'm in is my Unix course directory. Now I have other directories on my file system. And if you look up here, it's kind of difficult to see. But one of the directories I have is called research, and I put some of my research projects in that directory. So notice that this is also showing up in blue. All of the blue named objects up here in my list are actually directories. So if I'm in my Unix course directory, but I'm interested in seeing the contents of this research directory, what can I do? I can actually note that using cd ... means the parent directory relative to where I currently am. So in other words, cd ... goes back to where I was before. Okay, so again, I was in Unix course, and I can demonstrate that here using cd ... takes me back. All right. So the nice thing is you can traverse several directories. I'm going to go back to my Unix directory, and I'm going to show you that you can use the list command to see what's in another directory. So I want to list going back to the parent, from the parent traversing to my research directory. And I have 3 different folders in here. I have something called discrete R01, my presentations, and ordinal R01. If I don't like the way that's laid out, remember I can always use the AL option to provide my output as a list. So maybe I want to know, well, what is in my ordinal R01 folder? And I can see I've got more folders there. So you don't have to keep changing your directory in order to view the contents of where you are. You also don't have to move to specific locations in order to move files from a directory to another. The other thing that you can notice is that the tilde is a relative path. And so it's relative to your home directory. So actually, probably what I want to do is let's go ahead and let's change the working directory. I'm going to go home and I'm going to go to research, ordinal R01, and I'll go to the Bayesian directory. That way we're kind of in the situation where we're pretty deep, okay, into the file structure. So you can see my current working directory here. Now, if I wanted to traverse to the Unix course using the ... notation, and let's see if I can do this without making a mistake, I would have to go from Bayesian to the ordinal R01 to the research and then to Unix course. Okay. All right. So that does work. Let's go back to where we were before. The other thing that you can notice is that the tilde command means that you're always relative to the home directory. So instead, I probably could have just said cd tilde / Unix course. All right. All right, so just knowing the difference between absolute and relative paths sometimes helps you move along your file directory and subdirectory structure. All right, so let's go back home. And so I could also say cd tilde. That takes me to my home directory. I have a lot of files here. Again, we did copy these files from the home directory to my Unix course directory. So I really don't need them anymore in my home directory. So I can actually remove those. I am using a, and actually I'm removing some junk as well, just to show you that you can remove different things as you become interested in cleaning up your files. Just be careful. Had I not made a copy, if I'm removing them here and had not made a copy in my Unix course directory, they would be gone and there is no trash to retrieve them from. Now, some of you have noticed my ability to recall commands. I'm hitting my up arrow. So whenever you hit your up arrow, you can go and return to previous commands. If you've passed by the command that you wanted, you then just hit your down arrow. So that's a little time saver. All right, let's go ahead and clear this. And let's traverse to our Unix course directory. So now I'm going to show you how to actually look at some of the file contents. So we'll go back and see some of the commands to help you browse file contents. So there are various commands that can be used to explore the contents of a file. Certainly head is something that I use quite often. It's very similar to the head command in R. It shows the top 10 lines by default of a file. If you want to display a different number of lines, you just use the option dash followed by a number. You can also use a tail function. The tail function shows the last 10 lines of a file. If you want to show more than 10 lines, you use the dash n, where n is replaced by an integer. The WC function gives the number of words, characters, and lines in a file. Actually, it's in the number of lines, words, and characters in that order. So it's kind of like word count. More, this is a really nice function. It allows you to view the file linearly, but you're not accessing the file in a way that would make you edit it. So there's no chance that you can overwrite the file when you're using more. In order to go through the file, you can use the Q command and the escape command. The less command, it's very strange. I think these are kind of misnamed. The less command allows you to view the file just like more does, but it allows you to go back and forth through the file using the file arrow keys. Okay, so let's look at some of these commands in our Unix system. So again, we need to see what files we could possibly be looking at. I'm going to be looking a little bit at this 16s temp.fa file first. So let's look at the head command. Notice that it displays 10 lines. Now some of these lines actually are quite long, and so they're wrapping to our screen. Now I'm going to clear this, and we're going to use the head command, but instead of looking at 10 lines, I'm going to change my default from 10 to 20. Okay, so this is actually a fairly small file. And in fact, I can look at the tail of this file. Okay, there's the tail. Those are the last 10 lines. So I might be interested in knowing, well, what is the word count or the number of lines in this file anyways? And how many characters are in it? So notice there are only 9 lines. So when I was saying head, and when I changed head to -20, I got the same output. When I said tail, I got the same output. It's because there's only 9 lines in this file. It's very small. So I can look at the word count of, let's look at the other files that we have again. I can look at the word count in terms of the number of lines, words, and characters. And my other file called 16s microbiome reference file, this is a FASTA formatted file. So this is quite a long file. It's 14,090 lines. So this makes more sense to use a function like head. Okay, again, some of these lines are quite long, and so they're wrapping to my screen. I can also use the tail function to see the last several lines of my file. Now, these are really large functions, and so probably I want to use a function that's like either the more function. So when I hit the more function, once I've gone into the more function, I'm hitting my enter key to browse through that file. I can't reverse that. So I don't know if you can hear that. I can't reverse. Once I'm done browsing, I hit Q to escape that view. It probably makes more sense to use less for very large files. And the reason why is because I can use my down arrow, I can go back and use my up arrow. The other thing that you can do is you can hit Shift G. That goes all the way down to the end of the file. So less is very helpful in terms of really exploring the contents of a specific file. So when using less, you can go to a specific line by typing the line number followed by the lowercase g. Again, typing the uppercase G will take you to the end of the file. If you wanted to find a word in the file that you're viewing, you type a slash followed by the desired word or the character, and then you hit return. So if that is actually found, the line containing the word will be placed at the top of the screen. And if you want to find the next occurrence of that same word, you type the lowercase n, which stands for next. All right, and whenever you're done browsing through, using less or more, you hit Q. So Unix allows you to combine various commands together so that the output of the first command can serve as the input for the second command. And this is accomplished by piping. So if you remember from your tutorial on dplyr and tidyr, the piping command is a % greater than % sign. Here, the pipe is a vertical line, and it puts the commands together. So before we get to the piping commands, what I do want to show you are a few more Unix commands that can be useful. So some useful Unix commands are grep. Grep searches for a regular expression. Again, there is a grep expression in R, so there's a lot of similarity between certain R commands and Unix expressions. You do not use parentheses in Unix, however. So in Unix, the vertical line is the pipe command. You can also use passwd to change your password. CURL, it literally stands for see this particular URL that you type. We'll look at that. You can also use top for looking at the task manager for a Unix operating system. And you can use cat for creating and displaying short files. All right, so we're gonna use grep along with some of our other commands we've already seen in combination with this pipe command. All right, so I wanted to show you again a little bit about this 16S microbiome file. A FAFSA file always starts with the first line, beginning with a greater than symbol, followed by essentially what's a reference gene name. And then there's a lot of other fields, followed by another line, which is the sequence. And so you'll notice there's a regular pattern where you see this line followed by a genomic sequence. You see this line followed by a genomic sequence, etc. All right, so you might want to know how many actual genes are annotated in this file, and that would be identified by finding the number of lines that start with that greater than symbol. So I can say grep, and I can put in quotation marks the greater than symbol, followed by the file name that I'm looking at. And that's this 16S underscore microbiome underscore ref underscore file dot fa for FAFSA. Okay, now notice this is all scrolling to the screen. So that's a very unsatisfactory result. But what I can do is I can actually, let me go ahead and clear this so that it's nicely able for you to see. I can pipe the results from that grep operation, and then I can execute another command. So as I mentioned, I really want to know, well, how many lines are there? Well, we know that the WC command allows us to actually get that. So there are 7,045 genes essentially annotated in this file. We could have, instead of allowing everything scrolling to our screen, we could have looked at maybe the first 5 lines. We could have also looked at the last 5 lines, etc. So you don't have to pipe just one time, you can pipe multiple times. So for example, suppose that I want to use my grep command to find this, any line that starts with a greater than symbol. And let's suppose that I want then the top 100 followed by the last 2. So this is going to give me essentially the 99th and the 100th line of the file, okay? Because I said head 100, so I've got lines 1 through 100, but then I said tail 2, so then I get the last 2 lines of that result, which is line 99 and 100. All right, we did see that we could use the WC command to see how many lines start with the greater than symbol. We could also notice that there is a parameter to the grep function, which you would see if you used man grep. And that gives me the same result. Again, for WC, you have number of lines, number of words, and number of characters. This grep-c simply gives you the number of lines, which is a little bit easier to use. Now, I've been saying that we want to know how many lines start with the greater than symbol. I've been a little bit disingenuous in saying that this will tell me that. In fact, this will tell me how many lines has a greater than symbol in them, not that it starts with a greater than symbol. If I need to know for sure that the line starts with a greater than symbol, I need to actually precede whatever character I'm interested in starting with this, this like caret sign. Okay, I actually do get the same result, and I knew that simply because I've worked with this file so many times. So in both cases, preceding the greater than sign with that caret allows me to ensure that the line in fact does start with the greater than. So more sophisticated queries can be created by using the functions or the commands sort and cut. So let me clear this. Okay, so let's look at another file, and this is the D1E underscore genes underscore FPKM underscore tracking. Oops. Oh, let's see. I must not have that spelled right. Okay, there's not an underscore between genes and FPKM, there's a period. So let's change that file name. All right, so these are the first 5 lines of that file. Now, perhaps what I want to do is I want to extract specific fields from this file. So what's interesting about this file, unlike the 16S file that we were looking at, there's definitely a header row, okay? So we can see, we can see the header for this file. And perhaps what we want to do is we want to extract certain fields from this file. Okay, so I can use the cut function followed by -f, which indicates which fields I want. So suppose I want the 1st and the 7th field from this file. Again, the file name, I'm going to paste this in because otherwise I might make a typo. Once I've done that, I just want to look at my result. And so you can see that I've cut from it the tracking ID, which you can see is indeed the 1st field. So this is 1, 2, 3, 4, 5, 6, 7. And because there's so much wrapping, it's difficult to see which result here actually matches locus, but you can see the locus here. So you actually have in this shortened file that we just viewed, you have a tracking ID, which is kind of like a G name, followed by the locus. And the locus is in the format of chromosome number, colon, and then the actual locus along the chromosome where that gene is located. Okay, so we probably don't want to just look at it. We probably want to do other things to this file. So let's go back to this command. Actually, before we do that, let's clear. Let's go back to this command. We don't want to simply view it, but we have cut fields 1 and 7 from our D1E genes FPKM tracking file. Now what we want to know is we want to separate the fields using that colon delimiter. Okay, so now I'm going to cut I'll type this and then I'll show you what the result is and then explain it. All right. So what we've done here is we have extracted fields 1 and 7 from the file. Then we're going to cut the fields, but we're going to cut them using the delimiter colon. And when we cut the fields by the delimiter colon, we're going to keep the first part. So you can see that now I have the tracking ID followed by the chromosome number. All right. So we could have worked with our, oh, I do want to say that this delimiter has to be a single character. You can't have a multi-character delimiter for use. All right, so we could have processed our 16S microbiome file using similar kind of commands. So as I mentioned, any line starting with this greater than sign in that 16S microbiome file is actually an annotated gene. So after you have that line, there's a lot of different output that's piped together in a way, and I don't want to say piped, I guess this is a pipe, but the delimiter in that first line is this vertical line. So I want to use the cut where I'm cutting fields, keeping the first one, where my delimiter, again, is this vertical line thing. And then I'm going to pipe that to the command head. All right, so this just gives me the G names. All right, because once you have that first delimiter hit, it kept the first field. All right, so going back to this command, we're going to say grep, and we want any line starting with this greater than sign from our file 16S microbiome ref file. We're going to cut the fields, keep the first entry using this piping delimiter. Instead of using head, I now want to say cut F2, where the delimiter is this greater than sign, and now print. So notice what this did. It cut this result. So this was still the result, but the G name actually doesn't have a greater than sign in it. So we want to remove that. So we then just cut the field again using the greater than symbol, but we kept the second result. And so that gives us the actual G name. All right, so we can also sort by a specific column. So let's go back to our, actually, let me go ahead and just start a new line. It's going to be easier that way. Let's use the cut function where we're going to cut a field. We want to have the 7th entry, which is the locus. Oops. This is the D1E underscore genes. It's then a period FPKM underscore, oops, I didn't spell that right, FPKM underscore tracking. All right, so if you remember, the locus is field 7, and it is a chromosome, colon, and then the actual locations along that chromosome. So I've extracted that locus that's in that format, but I want to cut that because I want only the chromosome number. Again, the delimiter is a colon. After I have extracted the chromosome, I want to then sort the result. Okay, so you can see that I have chromosome 1 showing up here. Okay, the reason that's helpful is because I can sort it and then I can get the unique entries. So you can see I have chromosome 1, 10, 11, 12, 13. Because this appears in the locus, it does show up 14, 15, 16. So if you know biology, we have 46 chromosomes, 23 are from mom, 23 are from dad. So 2 of those 23 are sex chromosomes, either XX for females or XY for male. And so you have autosomes 1 through 22. And so that's why you're seeing these numbers showing up here. So if you wanted to know, okay, I want to know how many entries are there per chromosome. All right, so I've cut the 7th field, and then I've saved the first part that appears before this colon delimiter. I have to sort in order to count. So I sort those entries, and then I save the number of unique ones, but when I'm doing so, I count how many there are. So in fact, there are 1,866 entries that belong to chromosome 1, 1,498 entries that belong to chromosome 10, etc. All right. Let's go back to the top of the screen by clearing our workspace. So here, what I'm going to do, remember what we had seen with chromosome 13 is we had some 13 with a vertical line followed by some kind of characters. So it looked like there were multiple entries that were showing up in chromosome 13, but those they were not all being counted as belonging to chromosome 13 because they were unique. All right, so maybe we want to omit those and then make sure they get combined with those in chromosome 13. All right, so we have cut the field number 7, and then we've cut that one using our colon delimiter to save what's to the left of that delimiter. Now what we want to do is we want to add to that and cut. Again, we want to save the first part where now our delimiter is this vertical line. Okay, we want to then, sort that result, save what's unique, and then look at it. So as you can see, I have omitted those entries that have 13 line followed by NT, etc. characters. So now if I go back and I keep that information that I had before, and then I say unique C, I have the same number of genes on chromosomes 1 and 10, etc. But you can see this has changed to include those that weren't in the right format from before. All right. So another thing that you can do is you can sort by other components. Okay, so let's keep this. So that was sorting chromosome 1 followed by 10, then 11, then 12, then 13. Of course, that's probably not the most logical way to sort chromosome related data. So I've kept everything as before. I have the unique count, but now I want to sort, sort, and I'm going to say -K to -N head. Okay. So this is now sorting really by what is an alpha order. Okay, so the count in terms of the total number is in the first field. What I am sorting on is field 2. Okay, so you can see it's X locus MT. This is, I think, mitochondria, Y, unspecified. And then we have chromosome 1, 2, 3, 4, 5, etc. That's probably a more interesting way to sort your data. If I wanted to say sort -K field 1 -NR, this is going to sort my data in descending order. Okay. Now, the nice thing about these Unix piping commands, let's go back to this one. I probably don't want to simply view the result or even view part of the result. I probably want to actually output the result. So let's just route this, and the routing function is a greater than sign, and I'm going to call this chr count.out. All right, so I can use my less command to browse around my output, and it's really a short file, so I can see my output here. And so I've successfully processed a file just using some command line syntax. And in fact, this was just one line, and it really returns a nice result. If you have a file that you want to append the content to an existing file, you would use this greater than symbol. Again, this doesn't make a lot of sense, so it just took the first result and appended it to it, the second result. Sometimes you might process several files in the same way, and you're just wanting to append to the contents of an existing file. If you simply use the single greater than symbol, that overwrites this outputted file. All right, and the cat function will concatenate two files end to end. So let's suppose that I have this function, which again just gave me these results. Let's say that I also did the function where I sorted in reverse order. I'm going to say chr reverse out. So now we have two files. All right. I can say cat chr count, whoops, dot out, and chr reverse dot out. Okay, and that just put those two together. All right, so now we're going to move on to a different topic. So most of you will probably not be working with large text-based files unless you're working in the genomics area. However, you're probably more likely to be using R on a supercomputer to run your simulation studies. In order to use a specific software package on the Ohio SuperComputer Center, you need to load that package as a module. If we want to use R, we use the command module load R. If you need to use a specific version of R, suppose that only a certain specific version has a package that you're interested in using. You need to identify what packages are available on the Ohio SuperComputer Center by issuing module spider R. Either way, you can either start up the R session when using module load R, or if you've loaded a specific version by module load R / with the version number, then you can execute the R command. If you need to load specific user-contributed packages from the CRAN website or from GitHub, you can go to this website sponsored by the Ohio Supercomputer, which provides instructions on installing R, ensuring that R is installed into one of your local libraries so that it is available for subsequent use. Let's now go to our Supercomputer Center and look at what we're going to issue as commands. So I'm going to look at module spider R. And notice that there are several versions of R that are available. I want to use this specific implementation. And notice that when we issue that command, our Unix system has detected that we need other modules loaded prior to issuing our R command. So let's go ahead and load those additional programs that are required by R. So now we can load our R version 3.6.0. Now to start R, we just type R at the command prompt. All right, notice that the start does issue an indication of what version of R you're working with. What I like to do before I run any kind of batch file to the system is I like to ensure that the packages that I need are accessible within the version of R that I will be using. So today we're going to be running a script that makes use of the GLM path CR package and the Bootstrap package. Notice there's no package called Bootstrap because I misspelled it. But there is a Bootstrap package. All right, so we're good to go. So I'm going to quit my R session. And let's clear this workspace. So again, the files that I'm working with, we created these two. The other ones we had copied. But this GSE 3189 data set is a large gene expression data set. And in fact, it includes gene expression data for 22,215 probe sets or genes for 70 different subjects who have their samples classified as normal skin, nevi or nevus, and primary melanoma. We have an R script that issues the R code that we want to process. So let's first take a look at our R code. All right, so we load the library GLM path CR as well as the library Bootstrap. I highly recommend that your R command file load all relevant libraries and data at the top of the file. That way, you don't do a lot of processing and then get to the point of where a library is called, and if it's not present, then it hits an error. So you want to do this first. So in this particular data set, we have a response Y, which is an ordinal outcome. And the ordinal outcome is that the skin biopsy was normal, nevus, or melanoma. We also have our gene expression data, and we're going to log transform that. Afterward, we're going to use the GLM path CR function. This fits a lasso-like continuation ratio model using the GLM path base learner package. So we pass to it our predictor variables X and our ordinal response Y. Afterward, we're going to select a model. Here I'm just arbitrarily using that model which attains the minimum AIC as the model that's preferred. Then we'll look at which coefficients were selected by our minimum AIC model. We'll look at the names of those coefficients, their values. We'll also get the predicted values from the model. So we want to know how well did our model predict the true ordinal outcome. We do know, however, that when we predict data using the training data set, that we will have optimal performance. So we want to see what we would get as a type of generalization error assessment. So for that reason, we're using the Bootstrap package. The Bootstrap package has in it a function called crossval. Crossval takes the data as well as the model fitting function and a prediction function. So we have to write those ourselves. Once we've written those, and you'll see that these look very similar to what we've just done up here with the training data set, then we can pass to our crossval function the original data in terms of the predictor variables, the response variables, the model building function, as well as the predicting function. And we tell it how many groups we want the data divided into. So in other words, this is doing 10-fold cross-validation. Once the observations for the left out fold are predicted and saved, we can then do a table of our cross-validation results against the original observation Y. Of course, you always want to save the results in a workspace so that you can load the data into R later for subsequent plotting and other summaries. So aside from having the R script, which you may have already used R command batch to process an R script before, What we need for a supercomputer is a PBS script. So on the Ohio SuperComputer, a PBS script is needed so that we can submit our job or put it in the queue. The whole idea behind batch processing is that whatever you would normally type in at the command line needs to go into your batch script. The output that would normally appear to the screen goes into a log file. The system is going to then run your job when the resources become available. So this is a very efficient way of utilizing resources on the supercomputer. So again, what we need is a batch script for our job. We then need to submit the job, and we submit the job by issuing the command qsub followed by the name of our PBS script. If we want to monitor the job, we want to use the command qstat. There's a number of different parameters. I typically use qstat-u, which stands for user, and then I pass to it my OSC username. While the script is running, you can look at the output that's routed to the log file. And then once the job is complete, you can do any further work on the R workspace that was saved by opening R, loading the saved R workspace, and then performing any subsequent tasks. Again, if you're going to be doing large simulation studies, you want to make sure that you save your R workspace. That will allow you to then open your workspace, do plots, and put together tables. All right, so let's look at the PBS script that we've developed for this example. So there is a preamble to all PBS scripts. The first line usually indicates how many nodes you're going to use and how many processors per node. You also indicate the wall time. Note that the wall time greatly influences how quickly your job will be batched to the system. The longer the wall time, the longer it will take for your item to actually be picked up by the batch system and processed. So you want to try to estimate this to the best of your ability. You also want to minimize the number of nodes and processors required, because each time you issue a job, you are charged resource units. So your PI or sponsoring faculty member may need to re-request for resource units if you use too much of their resource units for processing your jobs. So try to estimate these as accurately as possible. One caveat is that if you underestimate wall time, your job will be issued to the batch system, processing will start, but it will stop when it hits the wall time. That means nothing will be saved. So you also have to indicate what account will be charged. You want to give the name of the job something informative so that if you need to monitor it, you'll know which job belongs to what job ID in the event that you need to delete one. These functions serve to really indicate whether or not you want to receive an email when the job has started and when the job has ended. If you're interested, you can always put together some lines that will echo to the computer to say what time the job started, etc. But as I mentioned, the whole idea behind this batch scripting is that you need to put in your batch script any kinds of commands that you would have normally issued at the command prompt. So we want to make sure that we take advantage of any user contributed packages that we've installed, like Bootstrap and GLM NetPathCR. We want to make sure that we load the appropriate software that's required to run whatever program we're using, which is R. We want to also use those packages that were installed. And then here, we're simply changing the directory to the node that issued the job. So we're just basically moving to the directory that the job was submitted from. Thereafter, this is something that you might be familiar with, which is our command batch, followed by the name of your R script, and usually we want to route anything to a log file, which we often call rout. So that's an example of a very simple PBS script. All right, once we have our PBS script and our R file created, all we need to do to execute that is to say q sub r example.pbs. Be sure to execute the PBS script and not the R file. To monitor your jobs, you can type qstat-u and then your username. You can see here that this indicates queue. That means my job has been queued but is not yet running. So I can check this a few times. Now you can see that that has been converted to R, and at this time it was running for 9 seconds. Another way that you can monitor your job is by issuing qstat-a followed by the job number. Your job ID is indicated in this very leftmost expression. You'll see now that it's been running for 30 seconds. So at this point, you could actually look at the output file. So as you saw in the R PBS script, after the end of R command batch, we have our R program, but we're having those results routed to our example.out. So we could look at what is currently in our command.rout or our example.out. So notice that you'll see the R version information that started up. You'll see if the library is loaded properly, if the data were brought in properly. You can see our output here. We actually do have already our table of the predicted class from the training data, the full training data set, and the class in our training data. And there were, very interestingly, no misclassifications. Of course, we do know whenever you apply any method to the training data and then assess the error, it's going to be a minimum. And that's why we're doing this cross-validation procedure. And you can see that the file is currently in the process of conducting the tenfold cross-validation. So once your job is complete, when you issue a command like qstat and check your user ID, you'll notice either a C will appear or sometimes nothing will appear. You can always check whether or not the expected objects appear in your directory. And we do have our R workspace saved. We also have our rout file that we can look at again. So let's look again at our rout file and see what happened. If you hit Shift G to get a capital G, again using less, it will go to the end. So we can see the total amount of time that our procedure took. We can also see that we had looked at it previously at this step. Once it finished, we do see that our cross-validated misclassification rate resulted in 5 misclassifications compared to 0 when we were just using the training data set. Notice that we did route our output to our example.r data. That's very convenient because once we have that, we can start R. And I'm going to remove everything just in case there's any stray objects in my workspace. And then we can load that workspace. And see our resulting objects. So this is the point at which you might want to do tables, graphs, figures, etc., in order to summarize your results further. Now, one thing that may happen is you might execute a PBS script, and then as soon as you execute it, or sometime while it's running, you might realize, oh, I don't want that to run. you're fine. What you need to do is identify the job. Notice I have two jobs that are currently listed. This one was the one that completed. This is the one that's been queued. If I want to delete that, I use QDEL for queue delete followed by the job number. So that way I don't get charged resources, or I don't charge my PI resources that would have been used had I allowed that job to continue. All right, so something else that I wanted to go into for a little bit is about file permissions. So you notice that when I did ls space -al, that each file and each directory had file permissions. So each user is part of some group, and user owner and group owner are identified in the ls-al listing. The format is D or dash, where D indicates a directory, dash indicates a file. And then we have RWX, which is read permissions, write permissions, and execute permissions. This first set, RWX, corresponds to the user. The second set, RWX, corresponds to the group. And the third corresponds to all other users on the entire system. So in terms of these permissions, they are assigned by a binary coding using the chmod change mode command. So for example, 000 in binary format is a 0, 001 in binary format is 1, 010 is 2 in binary format, etc. So you'll notice that if you have a value of 7, that means that all users can read, write, or that the specific person can read, write, and execute. So when you change the mode to 755, that means the user can read, write, and execute. The group can read and execute, but not write. And all other users can read and execute, but not write. So sometimes you might want to change the mode to 750, which means the user can read, write, and execute. The group can read and execute, and all other users have no access. So you can change the mode for each file by specifying the binary digits like this. So how do you actually set up a new file on a Unix system? So there are different types of command line editors, and those include this VI command, Emacs, and Pico. So each one has its own set of unique keystrokes for performing similar functions. So once you get used to one editor, you probably want to stick with that one. I have to say that I have used Nano for several years, and so I'm familiar with it. Other people really like Emacs and Pico. So if I want to create a new document, suppose I want to say new R. So here I can load any library that I want. I can load my data, and I can do a summary of my data. All right, if I wanted to save an image, of course this is not useful in terms of a practical application, but I could do that. And if I want to say the quit command, I can. I actually don't need that. And then I hit, notice these different commands down here. So I can get help, I can write out, read file, etc. If I want to exit this editor, I hit Control X. When I hit Control X on a Mac, it says save modified buffer. If I say no, it will destroy the changes. If I just say yes, then it does say file name to write to, and I can just hit enter, and it now saves that text that I just entered. So this is my file that I just, and so now I could actually execute that. So Nano is one type of command line tool. There are several others, and you just have to get used to whichever one that you're interested in and that you've used before. Sometimes it's necessary to retrieve data from an online database. And the curl command is a shell program that can directly access internet files on your behalf. So for example, we could execute this command, and when we do so, it will download that file to our account. So notice what it's doing. It's curl followed by the website, and then we're using this greater than sign to put the results in this file. All right, so let's look at this in our terminal window. So I'm going to say curl, and I'll type the web address, which is http www.rcsb.org/pbd. This is a protein database. Protein database files, and then the file name that we are specifically interested in is 1ema.pdb. All right, and actually, all right, so this is the command. So it doesn't look like anything happened. What I want to do is I want to route this data to an actual file. All right, so it looks now like something happened, and we can look at the contents of this file either using head, tail, or more or less. So it appeared that the protein database was no longer available. So I'm going to use a different data set. So if you're not familiar, Carnegie Mellon maintains a StatLib website. And one of the data sets that they have, this is a whole repository of data sets that you can draw from. This NO2 data set is a subsample of 500 observations that is from a study where air pollution at a road is related to traffic volume and meteorological variables. This is because of the Norwegian Public Roads Administration data. So the response variable in column 1 is hourly values of the logarithm of concentration of NO2 particles measured in Oslo, Norway between 2001 and 2003. And then the predictor variables, which are in columns 2 through 8, are the logarithm of the number of cars per hour, temperature 2 meters above the ground in degrees Celsius, wind speed in meters per second, the temperature difference between 25 and 2 meters above the ground in degrees Celsius, and wind direction, which is between 0 and 360 degrees, hour and day number that was recorded. All right, so if we have the link, which we can always click on the specific data set, and then we can copy that link. Within our terminal window, we can use the curl command, and we can specify the website where the data set exists. And then -O means where we're going to output the file to. And then we specify a file name. So I'm just going to name this the same name that it appears to be named in StatLib. So you can see now that something downloaded, and we can look at what this file looks like. All right, so that's how you can successfully download a file from the web onto your SuperComputer account. All right, as I mentioned before, if you start a job and then you recognize that there was some kind of an error and you want to remove that job, or maybe the job is going to either not run within the time that you designated, so you don't want to use up those resources, or you need to fix the job and give it more time to run. You can always use the QDEL for QDelete function. So you can submit your job, then you can check on the status. If you see the status of the job or something is not performing correctly, you'll notice the job ID, which is going to be in the far left-hand position, and you can just say QDEL followed by the job ID. You can also see what jobs are currently running on the system by using the top command. That will also give you an indication of your different job IDs. Now, once you've been in your command window or your terminal window for a long time, you might want to be able to recall the commands that you've recently submitted. So you can do that by using the history command, followed by a symbol that then pipes those results into a text file. And then to end your Unix session, you can just type the word exit. So here, and then I'm going to exit. So notice it logged out. I'm still in the terminal window. If I want to close my terminal window, I have to further say exit. So this is the end of the introductory overview of Unix commands and working with the Ohio SuperComputer Center. If you want additional practice, please visit the webpage on slide 8. If you do happen to use the Ohio SuperComputer resources, please be sure to cite the Ohio SuperComputer Center. The information is provided on this webpage regarding how to correctly cite them. Additionally, if you're interested in using clusters other than Owens, a description of all the clusters available and their full specifications are provided here.